rectangle business that we started with, and if you remember, we have this interesting thing about identities where we can take simple statements that something is the same as itself and somehow use the fact that other things that are related to it that are perhaps independent or one thing that's dependent on the others, and we can use that to build a law or build an axiom rather for something that can be stated as a law, and in this case just verifying what we already know to be true. Okay, so it's really simple stuff, but why does length times width multiplied together, whatever it means to multiply length and width, which doesn't make any physical sense, how do we justify that? And so our goal here is to justify the knowledge that we have, because that's one of the things about knowledge is they're justified true beliefs, if you go back to Aristotle. And so lots of people have beliefs, some of which are true, and some of those are justified. Okay, so you might have true beliefs, but you haven't justified them yet, so that means it's knowledge in one sense of the way we talk about knowledge. And so we go at it this way. And so we determined that the area was dependent on length and width, because area, if it wasn't for the fact that there were length and width elements, if there wasn't a perimeter, then there wouldn't be area. So when I write that symbol A alpha L and A alpha W, that's a proportional symbol, and it means directly proportional to. So you might recall from algebra you had direct variation, indirect variation, joint variation. Well, we have direct proportionalities, meaning this increases, then that increases. And we have inverse proportionalities. If that increases, then the dependent thing decreases, and vice versa. And so we'll use those same things that you did when you were learning direct variation and whatnot in algebra to build our laws. And so this will be one of the first times that we leverage that in our favor. And so since area was found to be directly proportional to things that are independent of area, things that constrain area, then we know that those dependencies give us something. So we can take these things, and since they're independent, we can write them as these quotient identities and use them to preserve identities. Something is the same as itself. And so if I take that identity on area, which is the dependent quantity in this game, all right, and we multiply those things together, and we get, or we can write A equals A per LW times LW. And so we get to this situation if A per LW equals 1, then it's true that A equals LW. Now this seems trivial, and computationally it absolutely is trivial. Conceptually it's not trivial, and that's the point. Okay? And the next phase of what we're going to do is going to be justifying this knowledge by means of encoding for the thing that we already have seen or think when we think of area, and that's if I have some unit squares, I can count the number of squares that are there if I know how many wide and how many tall, and the product of those counts would give me those square units. So if I knew how many inches the length was and inches the height was, the width was, then I could multiply the count and get that number of square inches in the area. You already know this, you've thought this, you've drawn it. We're going to justify that symbolically. So again, I'm not trying to teach you the formula you already know. I want us to continue practicing using this law-making, axiom encoding technique with something that's familiar. So that when we get to the things that are not familiar, you're not struggling with the tools, right? So like if it was the first time you ever used a chop saw, you know, those things where you'd be a little scared to build anything because you're scared of the tool. You don't know how the tool works. You're not sure how to press its buttons and you know, I'm going to cut my fingers off, etc. So that's why we've been taking some time to do it the way that we. So we started with the regular square where we had labeled the area and length and width, and now we're going to not label the area. We're going to pay attention to the length and width, and then this unit square idea that's on the inside, and we're just going to call its dimensions x. Okay, so there's some relationship that inevitably exists between L and X. And so just some unspecified unit of measure, it could be inches, meters, miles, whatever it is. It's whatever unit we pick, and there's lots of length units that we could pick. So it's, you know, number one, write identity statements for both L and X. Okay, so L equals L and X equals X. And, you know, what are we going to do with that? Write a fancy form of 1 for the unit length X. Okay, X per X equals 1. So the trick is why would X be the independent variable? Because that's what we've been doing so far. If I make a fancy form of 1, it's because it was independent. Okay? And fancy forms of 1 are always from an identity, not from an equivalence. That's some other form of 1. Well, the length is going to be made up of little chunks of X. There's some number of X units that make up that length. So that's the reason why L would be dependent on X. Notice before, the area was dependent on L. Now the thing inside of the box, this counting mechanism that we have for area, is independent of the length. So this is more parameterization. This in terms of that, and that in terms of the other, and that's the way we build stuff in science, and especially so in physics. So why we're going through these motions. Preserve the identity on L by using the fancy form of 1 for X as a factor. Okay, so L equals L, X per X, which means I'll get an L per X times X. So let's think about this, what this is saying. Apparently, the length of this rectangle can be, it's related to the length of these little, the sides of one of these little squares that make up the inside. Okay, that we already know the sum of all those little X squareds has to be the area. We know that, but we're not writing that at the moment. Well, remember back a few days or a couple days, a number is a whole part relationship written as a fraction. And we know that the length is the whole in this case, and X is a part of it. So that's a number. L per X is a number. It fits the definition of number. And so we could write it, L equals, if I wanted to call that N, you know, let N equal L per X. It's just a number, some number N. And we count, you know, N is a counter from time to time. So the length of this thing is some number of x lengths. Okay? You sort of already knew that. Probably didn't need to come to college to know that, but we're encoding for it symbolically. Again, it's just more practice. Well, we could go through the same motions, you know, next page. So if you turn to the next page in your handout, it tells you to do the same thing with width. And of course, this means that we would get the same thing here. Width would also be encoded as a number of x units, because the width is also the whole in that regard, and it's made up of some number of parts of this internal square that's going there. And so we could call this mx. We can't use the same label for the number that was on length. N might be equal to m if it were a square, okay, but that's a different matter. So we use a different label, just like the number 2 has a different symbol than the number 3, et cetera, et cetera. So we have different numbers that come from that. So we have L equals nx, width equals mx. So we've created, by means of this law, axiom, procedure, ways to describe more clearly what we mean by length and width. Okay? And so now, if these things were substituted for length and width, which is really what you're doing if you think about it, when you multiply length times width, you're really saying, oh, there's some number of meters times some number of other meters, and together that's some other number of square meters. All right? So we're just justifying our knowledge here. So that would give you all the answers 1 through 8. And then number 9 says apply these findings to the formula A equals LW. All right, so what might that look like? So I'm just going to write this out. And have you kind of take notes with it. So A, this is going back to our finding from the first lab. That's what we did the other day, the end of Monday. Is that way. And so now, instead of L and W, so I'll still have A per LW, but I'm going to import what we had before. We had NX for L and MX for W. And this gives us an A per LW in MX squared. We're still kind of up in the air about that A per LW thing. If it's equal to 1, then this all works out, right? And then, see, LW and M times MX squared, those are obviously equivalent. If this whole thing is balanced the way that we think it is, that we know it is, all right? So this makes our thinking explicit. And I hope you see that at minimum, that N being the number of unit squares inside of this along the length L, and M being the number of unit square lengths along the width, that the product of those two numbers counts all of the unit squares, and then the unit is that x squared part. Okay, so just to be clear in this video, this product, okay, is counting unit squares. Whereas this, well, that is the unit squares. And pretty much at this point, this justifies the thinking that we brought to college with us. You know, in high school, junior high, somewhere, wherever we first encountered area, you were doing this on a piece of paper. And so that would be like part of number 10 there. Interpret this new equation by identifying the parts of the quantity that are described for what you obtain in this product of LW. So we've basically answered 9 and 10 in the handout there. And now we're going to try to deal with the rest here. And so all are part of what I'm going to write here will finish the deal for us. So another way that we can look at this, and I'll just write this out. If I leave, instead of writing it nx and mx, if I leave it like it originally was, where I had L per x times W per x, okay? So making the whole part relationship of those numbers n and m explicit. So this was, that was n and that was m from before. So if I bring those back in this way, then I'm going to get A equals I guess I needed to, I'm sorry, this would not be in here. All right, I'm going to kind of move this over a little bit. So erase that. Okay. So those L per XX and W per XX, those were L and W. Okay, keep that clear. So now I could write this A per LW times LW per x squared times x squared. So just to be clear, this x and this x are making that x squared, and this x and that x are making that x squared, and LW is obviously itself. Well, again, this can be rearranged, so we're just taking advantage of arithmetic here, okay? And I could have A per x squared times LW per LW times x squared. And of course, this would work out to be A per x squared, x squared. But let's think about what this would mean right here. Area, the space enclosed by these perimeter elements, is now written in the form of a number, or this is a number, area per x squared. The whole is area, its parts are these square units. So now we've justified symbolically our prior knowledge that we did by hand all sorts of times before college. right? And it's a count, it's a number. That relationship can be expressed as a number. There are some number of x squared units in this thing called area. And those x squared units are now related to our length and width. Hence, now we've justified, at least all but the final part of writing out an equivalence, that this way of this LW parameterizes quite well unit squares that we use when we think of area. The way we measure area is now symbolically, logically justified. All right, and that's really all that this is about. Is the symbolic language encoding for what the law already described. And the law in this case, is there a law of area? Yeah, if I increase the length, the insides will get bigger. If I decrease the length, the insides will get smaller. And so we are talking about the relationships that define or quantify bigger and smaller. And that subtle step is a really important step, because you can look at it and go, if this gets bigger, that gets bigger, et cetera, et cetera. But now I quantify it. This formula quantifies what is obviously true. And so think about it. You make an observation in science, or you look at the history of science. Here's this thing, keeps happening the same way every time. How do I quantify that? And so whether or not everybody who invented all the laws of physics or chemistry or whatever did it this way, which I don't think they did it something like this, but because they come up with the same formulas that we're going to come up with. So their thinking was somewhere in here, but if that was ever known before me and my old grad advisors came up with this system, it never got written down. Or if it's written down somewhere, it's hidden. Okay? It's under a case of fossils or something in the back room of the Smithsonian, and nobody's found it yet. You know, Newton's secret chest of toys or something. So there we go. So really, in this sense, here we have come to a point where A per LW times NMX squared is the same as A per x squared times x squared. And really, what that boils down to is A per LW equals A per NMX squared, which means length width product is now understood to be the count, because that's what N and M are, they're numbers, of these unit squares. And so we justify our definition, and so this implies that, you know, A per LW is indeed 1. This is a definition that just got justified symbolically.